Okay, yeah, because
You're
it
now
doesn't
recording.
allow me to do
Not a
that.
problem. Yeah, I've done that. And now, should I make Nitash the host? Nitash, you'll stick around for 45 minutes?
Yeah, it's 25 slides.
Nitash
Hopefully, it may
Balsara.
not be that long.
Okay. Nitash Balsara, are you here for the next half an hour?
Yes.
Okay, so I'll make you the host.
Yeah,
And then
I'll
if you're
stick
leaving,
around anyway, even if
okay,
I'm
good.
not
And
sticking
if you're
around, so
leaving,
don't worry.
make Gary the host. Gary is also well aware.
Ooh, what happened? Did
Now
I?
you're messing around, Sunder.
Yeah, what have I done? Ooh,
Yeah, you're messing around.
do you see this?
You're
Yeah.
now
Now we
sharing your
don't see your,
emails
we
with
see
us.
your email now.
Oh, hell. What did I do? I was trying to advance the slide. Okay. Go back to share. Oh, wow. Sorry. This is ridiculous.
Not a problem.
Share. Okay, share. Okay. Desktop one. Key. Let's see if it goes in here. Okay.
Now it's good.
Okay. Now it's good. Now will it? Okay. Yeah, I can now move. So I couldn't have moved. I
Okay.
wasn't able to move. Okay. So I'm going to, maybe because we started so late, I really apologize for all this. Okay, it's so nice to see everyone here. See, we have a fairly small thing. So I'm going to talk about corrosion inhibition and sulfur deposition prevention in high H2S systems. And it's pretty important because people have been producing in high H2S systems from early 90s or even from early 80s, actually, or late 80s. And my company has had a lot of success in working. So we have been one of the earliest and some of the highest temperature wells. So in Mississippi, there is a certain formation which got down to about 500 Fahrenheit. And we have been treating, or we were the initial people, our competitors are perhaps right now in, but Shell started producing these facilities which are extremely high temperature and high amounts of H2S. And these fields are, and the context of why this is important is there is naturally hydrogen sulfide present in a large number of oil and gas wells. As you go lower down, when you reach 150 Fahrenheit, and if you're in a limestone formation, you will get huge H2S. So when you go in different fields, and let me give you examples. For example, Qatar, or if you go to the Gawar, there's the Kaf formation. If you drill lower and lower down, once you pass 150 Fahrenheit and you're on a limestone, this thing, because of thermochemical sulfate reduction, the sulfate gets reduced by organic material to H2S. You have large amount of hydrogen sulfide. Now, hydrogen sulfide is extremely poisonous and extremely it's a very, very dangerous gas. And to give you examples, just last year, someone in a PMAX, Deer Park, which was a Shell refinery, it was sold to PMAX, and someone when they were cleaning, they opened up the wrong valve, and 4 or 5 people died in a very, very this thing. So even above 40 ppm, 40 ppm is start to be IDL. 10 ppm is you're dangerous. You have all alarms going off here. 40, 100 ppm, you can die. And so it has to be handled very carefully. However, and this is why I've talked about this, is people may not be aware that really you can produce fairly successfully in hydrogen sulfide systems. And hydrogen sulfide systems, in fact, if you would go to ExxonMobil's webpage, it's one of their major important production, this thing, is that they can operate in hydrogen sulfide. So now the Mississippi wells are basically, this was a shell facilities, and from 1992, these wells are present. In fact, at one time I had done some work on it. It was a Board of Education well, which means it was owned by a school district around Jackson, Mississippi. In Canada, the Western Sedimentary Basin has tremendous amount of H2S. And really, in fact, we had, basically protected a place from 1968 to end of life in 2013. And it's right next to Calgary Airport. So whenever you go in, you can go into Calgary Airport. And if you go into it, you'll just basically see that. And that's actually the Nixon Balzac field. That's this thing. And Tengiz is also a high H2S facility, which we are this thing. And Exxon operates a LaBarge, Wyoming. This is in between Salt Lake City and Yellowstone National Park. And if you go in between, there's a 40-mile pipeline, which is 65% CO2, 5% H2S. It's fairly difficult. So there are a lot of challenges in sulfur, and challenges in sour gas production. And basically, when you're developing a field, it is most probably 3 times more expensive if you have H2S. And one big challenge is kind of the type of metallurgy you can use. So you can use carbon steels, but they have to be resistant to sulfide cracking corrosion. And generally, the things that make a steel strong are things that make it susceptible to sulfide cracking corrosion. And then only after that, you have to go all the way to Hastelloy, which is extremely expensive. So there are these sort of difficulties in just the capital cost. Now, when you have high H2S, the phase equilibrium is kind of interesting in the sense you can get sulfur deposition, and sulfur deposition can cause very bad corrosion. So really, you're worried about low velocity lines, and under deposit corrosion is very bad. So generally, when you have H2S and it's flowing very, very fast, you don't really have corrosion problems. When you're going slow, you have problems. All of, generally the corrosion problems with H2S is pitting corrosion. And I'll talk about some of our electrochemical autoclave techniques. And again, I won't go into it. This is a little bit of a salesy about our global technical this thing. But we are the premier supplier of corrosion inhibitors in high H2S systems. We do, for example, Qatar condensate can be extremely corrosive. And a lot of these, so a lot of your major facilities which have high amounts of H2S, we protect them. And so again, I've gone through this, production and capital costs can be substantially much higher. And you can have sulfur deposition problems. These are really, and if these it's the deposition, and you need to control that deposition. And basically, sour gas will increase because we have basically drilled most of the low reservoirs. And the deeper you go, the higher the H2S. In fact, if you go to particular fields, you'll see as you go down. So we have used these to enable people to use less expensive materials. And carbon steel has been using from the 90s, from the 80s. And sometimes there's not great awareness of this. And this is the reason it's there. These show our experience where we have worked in a 90% H2S field. This is Exxon LaBarge, 65% CO2. We have in a range of applications, and you can see different chloride levels, different liquid production. We do use, in many of these cases, you do use, when you do corrosion and you look at corrosion, oxygen corrosion is most probably the most aggressive. CO2, H2S is a kind of very, very, you get pitting corrosion, and you do need higher concentrations of the inhibitor to work. And so this kind of shows our the different places where this works. And again, as I said, high H2S is there in many, many fields. In the Indian context, perhaps in Cairn Energy also that is seeing some sort of H2S, but not as much as many of these fields. This is this is the application in Thomasville, which is in Mississippi. And what was done here was basically you put an inhibitor in. It was very, very important to determine the right phase and have a oil which doesn't flash out at 500 degrees and would carry the inhibitor through. You can see that the kind of wells are 29 to 45%. You know, you can see also in this system, this is the kind of system in which you need. And these have been very, very successful. They're expensive, but putting in with an oil carryover system was the way in the 1980s and 1990s that people chose to protect them. Again, Shell, this is a Shell facility, which you're seeing that this thing, other thing is Exxon. Again, the Mobile Bay production is here. And very few problems, but it was very, very important to have this phase stability and the choice of carrier oils to be extremely, be done very well. If you don't do that, you have problems. So again, this is the example for us where it's Bearberry and it's in Canada where we have protected 90% H2S. The problem right now, in the old days, there was a time when you really wanted to have sulfur. And the sulfur would be used in in fertilizers. Nowadays, it's difficult to, although you recover sulfur, the sulfur is not so, I mean, fertilizer production prices are not great. So sulfur, I think, sells at about $40 a ton or something like that, which is very, 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 very cheap. And so that's a problem. So then you don't want to really get into this. Again, one future area of thing could be that there's lots of H2S in the ground. The dissociation energy of H2S is 1/3 that of water. One could think of a hydrogen economy relying on H2S and decomposing the H2S to sulfur and hydrogen. That's possible, but right now no one is doing it. There's no technology, but that's an area of technological interest there. So again, when you have sulfur deposition, it's a significant cause of corrosion and this thing. Basically, you have this sulfur saturation point is exceeded. Again, you're bringing up a high pressure well. In a high pressure well and high temperature, your sulfur is soluble in the gas and the oil, and often the gas is working as a supercritical thing. So you get a lot of sulfur there. As soon as your gas lowers its pressure, the solubility goes and you have deposition. And when this happens, this is where you can get extremely severe corrosion. This needs to be avoided at all costs, and one needs to have appropriate sulfur solvents and sulfur dispersants. I mean, there are sulfur solvents which have become fairly, problematic, and they're very kind of carcinogenic and other things, and people are having certain dispersants which they use here. So again, how do you prevent sulfur deposition? So again, sometimes hydrocarbon itself dissolves sulfur. So if you have lots of hydrocarbon, you may not have this problem. But, and again, you can sometimes use or inject an appropriate hydrosolvent to do this. But there have been many hydrocarbon solvent packages, which have done this. And these dimethyl disulfide and diaryl disulfide have been used to remediate, but these are extremely corrosive sort of substituents. and we have, amine-based solvents and dispersants, which alleviate these sort of uh, deposition. And so this is the case. This is actually the Nexon-Balzic system. It was the lines, near $1 million houses. You were seeing, these lines with 23% H, 32% H2S is high. And, we had been, we have protected that system till the close. It closed. It was, Nexon was bought by CNOOC, I think partly just for the reason of how do you deal with the H2S in your systems. And we had a kind of asphaltene sulfur dispersant to move to do this. In a lot of this, it's correct chemistry, and it is also the people involved. You need to have people who are monitoring, who are looking at the system and keep on looking at that. So again, we have again in Canada, you can have Canada, Tengiz, all of these, Abu Dhabi, you can have these sulfur deposition problems. And again, using a correct sort of solvent at the point and looking at the solubility of its phase, this thing, behavior, you can find sometimes, again, ideally, really doing something thermodynamically is expensive. So you kind of do something in which you can keep something in dispersion or something like that, because that's the cheaper solution, and that's what generally industry does, just so you do it consistently and you do it properly. So again, we have a whole bunch of solvents. We're big players in the Canadian market, and we use these all the time. Again, these are different fields: Pengrow, Nexon Balzic, which I showed you, which is fairly, again, Nexon Balzic is right. It's you see the place from from Calgary Airport. And these are all different sort of in this thing. The Western Sedimentary Basin of Canada is full of high values of H2S. But if you drive up to Banff, you'll see several areas where there are several places where people had been producing natural gas in those areas, which was high sulfur containing natural gas. This is an example where we, again, from 1986 onwards, we have been protecting a 40-mile pipeline. So the original story at the beginning, people did not think one could basically inhibit, and there was difficulty. It's difficult to procure high alloy steel, and this pipeline. So because they wanted to start, they had done a lot of experiments had been done on the corrosion inhibitor. So they just put a carbon steel pipeline so they could produce, with the expectation that this may corrode away. This system, which is 66% CO2, 5% H2S, it was the second largest helium production facility in the United States. It has been producing from now, it's still producing now without any sort of problems. And commercial production in that area is 720 million standard cubic feet of gas. We're kind of very proud. This is a joint Exxon and Baker Hughes publication. And this is the same thing. It shows basically in fact, at one time they decided to reduce concentrations, and that's why they had these problems here. And we have been, this is kind of the values from the early 1990s to, I think, 2016 or 2015. And basically we've been protecting. In fact, many people, Exxon engineer once told us that, you can inhibit this, you could basically produce any system with carbon steel, actually, just get availability properly. But it's not always that easy. But this is an enormously, 65% CO2 system is very well. In this facility, actually, the CO2 is separated and it is actually injected in the ground, or it is recovered and used for enhanced oil recovery all over the Wyoming area. So again, you can these were Board of Education wells. Look at the depth, 6 kilometers below the ground. Again, 201 centigrade, extremely hot systems, high amounts of H2S. So in all of these systems, what you do when you are going to try to protect it, you must make sure that you have a liquid stream present. And so again, one uses simulators and other things to ensure that you have a liquid this thing. And some of our parts of this, I remember in this sort of thing, is how much water do you put in in the application. It's important to know that so that so you don't get the whole thing evaporating out. And again, like, again, we've all learned material. For me, being in the additive business, material balances have been is something is a go-to whenever there's a big problem. Whenever if your additive is accused for about anything causing precipitation, causing something else, the first kind of thing you do is you do a mass balance, and it's so important. So all these basically for me, my basic chemical engineering training, which was excellent, was very, very helpful for me in all kinds of things. And I look so-called in here, very, very this thing, but it was really basically basic thermodynamics, basic chemical engineering to understand it. And here it was very important to figure out what that water film will be. And again, the importance of all of this is that definitely in the United States, we are producing a lot of oil and gas with in very dangerous conditions, but it has been handled by the industry well. It's handled very well when it's when professional people are involved. And even when it goes to smaller companies, as long as that care is exerted in the facility, you don't have problems. In contrasting in United States, here it's basically you're worried about lawyers. In Canada, the regulatory agencies are really, really good and really helpful also. So again, this is a case, I mean, again, for me, when I was young, I think in my first undergraduate with A.K. Singh, I said about, complained about analytical chemistry. We use analytical chemistry all the time for this thing, basically these are samples where you take the sample and you do inductive coupling, plasma atomic absorption spectroscopy, and you find out the manganese and whatnot, and you then look at the ratio and find out what those are to see how much these work. And we use it all the time. So I always, again, I regret a lot of the things that I really made a, big fuss, which I shouldn't have really. So again, this is okay. The 3366 was extensively used in Canada, and it's used in Tengiz, or it had been used. It recently we changed this thing, but it had been used in Tengiz also in the Kazakhstan fields, and these again have been. I mean, we did a lot of work. So to reproduce pitting corrosion is very difficult, and in fact, in the project that created this, we had to spend a year to kind of reproduce the pitting corrosion, to figure out mines of method producing the pitting corrosion. And then after that, once we find a method, we find something going, then you just go and test a whole bunch of things. And we tested and we found out, what would be, and this is a very, very popular inhibitor all over. So again, in low velocities are the leading thing. So your pipeline should be traveling at its sufficient velocity that small particles are not depositing out. But many times what happens with time, so this is tough on the in the oil field, because with time, you're not able to maintain that velocity because you don't have that production. And you can create, especially in H2S systems, create heavy. The reason you're getting, in these cases, the reason you get the corrosion is the iron sulfides are semiconductive and semiconductive, so they create galvanic effects. And it was hard to reproduce, to get test methods of recreating corrosion. One of the ways what we did is in anoxic environments, and you have to be very careful. You want to have your facility and you're completely oxygen free at very low amounts of oxygen. You then create mechanowhite, or you create this thing. When you introduce it, and here these are interferometer this thing. So you can see this is a case where it's nice and smooth. But you see all of these are extremely, you see tremendous pitting. These pitting were when we introduced precipitated mechanowhite. And by doing that, you see the problems. And so it gives you also a nice test methodology for testing what can relieve it. And part of the test methodology may not just be inhibition of the system, it could be also solubilization of these sort of things that are causing problems. But and that may be part of that formulation, and you'll see that. But these are, I think, very nice work. My colleague had done some very nice work, which where you see these sort of, see the problems. And it was not, I don't know how well people appreciate this in our industry. So again, yeah. So again, under deposit corrosion is there. There are different ways of, it's really important in actual, again, operation to kind of clean your system. There are, there are galvanic means of looking at these. And again, so sometimes also in some of these studies, the corrosion inhibitor the when you apply, the corrosion can be increased. Now I'm not sure whether these are always, no, these are not artifacts. You have to be very careful. So again, a lot of the point of really maintaining a system in high H2S is to prevent the deposition. So again, it's predominant. Pitting corrosion is what causes failures, and you need to have proper methods to select those. And we developed things which, without using any sulfur, it took a long time. This took about a year just to figure that out, by Sean and company. And so really we looked at different ways of penetration, and we used that to develop products, and actually the 33.6. So one ways of doing it is simply you put your coupons in, you take them out, you wait for, it could be 7-day tests, take them out. We also developed an electrochemical technique, and what this electrochemical technique was the following. So whenever pitting occurs, so normally your system is at galvanic kind of equilibrium. So that in our CO2 systems, they're just above the iron to iron 2 plus, where it is on the galvanic series. If you see a big bump in potential, that very much can be, or that's what we think is a initiation of a pitting event. So we have a kind of software that when we see a big bump in our corrosion potential, then we do LPR and we see what the corrosion rate would be. And then you can count these. And again, we have had a patent and other things on this. We can count where they are. And actually there was very nice work which was done by colleagues of mine, in which we can associate each one of these pits with actual, when we see the images. So we really had a nice advanced electrochemical technique of kind of determining. This has actually not been developed so well because of a whole bunch of other well, I don't know how, again, perhaps us and our, my guy who did this also went to our competitor are doing it, but not many people are really looking at it. It's a real kind of neat technique, but you have to know when the potential free potential changes and then record it, and it is what the beauty of it is, in situ you actually have a means of determining pitting and when pitting corrosion is, and that should be very valuable. And so we use that for one of these products, which I said has been used all over the world. It was used, these are the first places here. So with that, again, I was, Baker Hughes, we have, Sugarland. We have a lab in Liverpool. We have a very nice lab in Dhahran also. And we test deep water facilities. And I think with that, I think I'm here more, it's more, okay, I don't know what I have that topic. This is mistaken. So, thank you very much. I hope I hope it's not too boring.
Not at all, Sunder. Thank you. I think people can just speak up if they have questions.
Yeah.
And I want to
Yes.
commend you on, on a very sort of punchy and brief, overview of these issues.
Okay, thank you.
Yeah.
Thank you.
Yeah, I like the short presentation too, punchy and short and sweet. Talking about sweet gas or sour gas or whatever. But anyway, I mean, so what is the typical lifetime of these plain carbon steel material in these aggressive environments?
So at Chute Creek, actually, in the Wyoming, 1986 to now.
Wow. Okay.
Yeah.
Okay.
Again, with wonderful operating team, ExxonMobil and us. ExxonMobil keeps us on our toes, right? So we do the right things. Okay, how bad can it be? With sulfur corrosion in 2 months, 3 months, you can have disaster.
Okay. Okay.
So,
That's great.
again, so that's the difference between good performance and bad performance, and that's one of the reasons why a producer like ExxonMobil, you look at its website and you'll see that it prides itself on that's how it produces.
Um,
Qatar, the RAS gas, the first things were all with ExxonMobil actually in the production there.
So Sundar, how about the more high-end steels, and also, I mean, nickel-based alloys? For
So
what kind of oil
you have
industry,
to go all the way to C276. So that's
yeah,
the real problem. So in CO2, 13 chrome is kind of, wiped out. You do a well completion, let's say BP will do a well completion in 13 chrome, and they don't need us. But in sour systems, you okay, some places, some in the early, like Mobile Bay has been operated from 1980. It was sold to someone and all that. They earlier would put Hastelloy down on the bottom and then carbon steel up. But you can imagine, for example, the 40-mile pipeline with the carbon steel with the Hastelloy is going to cost
sure,
gazillion dollars.
sure.
So it's
Okay.
not. It's not. So this is the thing, and this is the point, and this is why people use us. That's for an Indian audience. This is, why you use a company like, which has labs and has experience in this. It is hard to do. Now, there, with time, but we try to keep everything secret, so, whatever. So whatever we do, and a lot of our things are also, some of the successful things are things that are grandfathered in, if nowadays, if we had to get EPA approval, we could be dead on them.
Yes, I understand for the pipeline. I mean, not in the wells, but I mean over land you would use carbon steel. But I'm thinking in the wells itself you're using carbon steel for these environments. I mean, it's
Yeah,
basic
you do,
101. Okay. Yeah.
you do.
Okay, great. So my question was,
Yes, you do. And again,
yeah,
remember, again,
yeah,
but even you do it you do it because of the, you see, again, because when you're going down deep, you have this question of strength also, right?
yeah,
So again, where a lot of people are now doing is how do you manage the strength of the alloy with respect to the H2S? So the deeper you go, so let's say like, okay, so 95 kpsi yield strength, people want to go to 120 yield strength, and the 120 may be problematic. So the, like all of the Tenaris, everyone is trying to build a better type of a stronger steel, which means more cementite, right? More carbon, but
sure.
not getting sulfide cracking corrosion resistance. And that's why in NACE AMPP, MRO 175 is a huge business, right? It's a very difficult, you know, the standards are really, everybody is fighting on the standards. Yes, Sundar.
Thank you, Sundar.
Yes, Ramachandran. My question is not directly related with your subject, what you said just now, but since you're talking of oil wells and gas wells and so on, do you have any idea of how this carbon dioxide that is removed from various systems and
Mhm.
how it is sequestrated, how deep it can go, and how does it remain there? Have any idea on that?
Yeah,
Because
okay.
UK is trying to
I
sequestrate a lot
mean,
of carbon dioxide.
so what you're trying to do is in carbon dioxide, you're putting it in. So, I mean, you have a lot of pressure. The deeper you go, you have the lot of pressure, right? It's density times the thing. So, there's a lot of saline reservoirs that could take a lot more CO2. And if you put the CO2, you see, okay, what are you worried about? When you're pumping CO2 in a saline reservoir, you're worried about scale formation, right? Calcium carbonate formation. But you have the temperature and you have the pressure. What does the pressure do? The pressure gives you acidity. CO2, becomes carbonic acid. So you have to work all these things out. Again, sometimes people would like to have mineralization, but you'd like to have that mineralization right not on the well, but way out there. And that's where a lot of people are trying to get where the mineralization will be. Does that answer your question? And
No,
how
I'm
big
not.
this is? This is it's fairly so in carbon capture and sequestration, maybe 20, 30 years or 100 years of our fossil fuel CO2 could be there's sufficient sequestering capacity in reservoirs. The tonnage that would be involved would be huge, and the industry is nowhere near where it needs to be in doing that. And actually, I can talk a lot on CCUS, but I mean, again, I'm doing, I have I'm giving a joint
So,
interest
in short, what you're saying is the gas, CO2 gas, which is being sequestrated, which is being pumped inside at high pressure into an oil well,
into
that
a
becomes
saline
a
reservoir,
gas well, that becomes a
water
liquid.
reservoir, water, not this thing. You've taken out all the oil. You've taken
Okay,
out
so
the
nothing is
oil,
there. So
right?
it changes its phase into liquid. That's what you're saying?
Depending on the temperature and pressure, right? Depending where it is on temperature, pressure, or it becomes carbonic acid.
Okay.
Becomes
Yeah,
carbonic acid.
I was
It becomes
wondering how,
carbonic acid, bicarbonate. Carbonate, it most probably precipitates out, but bicarbonate.
and it
Bicarbonate.
will not come out again. It will not come out on its own again.
Okay. It can come if there's seepage, if there's means. Again, this is under high pressure, so the whole question is evaluating cap rock, evaluating porosity of the rock, of the formation, and which is makes old natural gas may be completely punctured and bad, may not have. So you'll have to look at the rock. It's not my area, but that's what you'll have to
Okay.
look. And people do this also. We put little sensors all over the place to see what that is. So people
Okay.
have already done it in certain, like in Illinois, DOE had a even 10 years ago, they, did a pilot plant where you saw you saw they monitored the reservoir and saw that, everything was there. Yeah.
Okay. Okay. Thank you. Nitash, you can close it if there are more questions.
Any other questions or comments to Sundar? Hey, Sundar, I have a question. When you talked about your open circuit potential bumps,
Yes.
can you point to what a bump is and what an error is on the plot that you were showing?
So the bump is when
That's
it moves up. Oh, you
slide
want
21. Yeah.
Yeah, that may be a.
Where's the bump and where's the, I mean, it could be noise also, right?
So the red is corrosion rate. Blue is E-core. So blue is that. So the blue is your bump. See that here at about 1,000
Yeah.
seconds here. Here we had a whole bunch of things here. Here we had, here we had, here we had, and then in the software, I mean, the guys will say what that delta V will be.
Mhm.
So so what we're doing, what is done is one is you're measuring E-core, and the corrosion rate is measured by linear polarization resistance, which means you're adapting. So, gee whiz, how do you do this? That means you have to have certain, this is, you can see this is 20,000 seconds, but really this is discrete, because there are points where you're sampling the potential. Then there's another point where linear polarization means you put an applied field. And actually, the assumption is you're all at equilibrium at that point, right? And then whether that's there, not there, who knows, that should be better. So then here it gives you a corrosion rate. You can, convert to Faraday's, convert to iron, get you this thing and get that, see if it works.
Cool. Thank you. Any other questions? I have a non-technical question, Sundar. When you win your next trophy, are you going to take the ceiling and put it higher or reduce the height of the bookshelf?
Oh, these are no trophy. These are just bookshelves. I need to clean up. I have all these old National Geographics. The trophies are all my daughter's actually, so that's more
Oh, how
not
nice.
mine. There's so many, and she wanted to get rid of them. We don't have the heart. We just keep them, It reminds us of her.
So Sundar, another non-technical question. So, I mean, have you visited a lot of these oil fields? I mean, from Kazakhstan to other parts of the
Yeah,
world?
yeah. So I've
Yeah,
not been to
yeah,
Kazakhstan. I've been to
yeah,
Russia, to Astrakhan. I've been
yeah.
to, so I mean, again, I've been to, I mean, all of Canada, a lot of times I've been to Canada. I've been to, oh, in 1999, I was at Prudhoe Bay in February, where it was minus, 40, 50 below, and I had to get, again, most of the time I'm being shown around as this, this computer guy really, or not, whatever, not really the guy from Houston, actually. So all our guys are right there. So yeah, I've been to there. I've been to this thing. Then Netherlands. I've been to the Groningen field. Then a lot of the North Sea, and then I've been offshore on the Tapti platform. Actually, we did a drag reducer trial. Yeah, right now my company is 60% of the add 60% of any petrol you're getting, 60% of it has our additives in it. And 40% of the oil from Gulf of America is Gulf of America, yeah, who knows, whatever we call it, is our drag reducer is used. So on one pipeline we are using our drag reducer to get more oil
So,
out.
any business in India? I mean, offshore
Yeah,
Mumbai or
we do,
anywhere
but
else?
it's very hard. I mean, again,
Yeah.
like Sundarajan, and I mean,
Okay.
yeah, we have we did with Yeah, we supply, no, we're the sole suppliers of Cairn Energy right now.
Okay.
Cairn Energy, yeah, we have won a tender, maybe it's 1.5 years, and then, then they kick us out or whatnot, You're right. I'm here, it's a little bit, I apologize. This is kind of, I just cut and took one of my own, this thing, you know, my presentations, but it's a little bit salesy, so I'm sure the competitors will say, they're better or whatnot. I don't think they're better, but that's
Thank you, Sunder.
Oh yeah, Shailesh has a question.
Yeah, I'd like to learn how a corrosion inhibitor inhibits corrosion.
Yeah, so okay, I have a theory. So again, it depends on there are different types. If it's doing it at very low concentrations, I propose something known as the self-assembled monolayer theory of corrosion inhibition for imidazolines, which imidazoline is one of the important ones. And that is what happens is it binds to the surface or binds to the oxide layer on the surface. The binding can be such that they form a self-assembled monolayer. That is, the oxide structure is structured, so the binding will be also structured. And then you have a hydrophobic tail that prevents that. Now, this is true for oleic imidazoline. For others, it may be different. Other people also have, in other cases, you have film-based, which means you have much more, you need more inhibitor, where you actually make some sort of film that is kind of retardant of the corrosion.
Like a passive layer.
Yeah,
Passive,
yeah, passive layer, precipitant. But since like the imidazolines and all will work at 10 ppm, they're very low phases. So this was what our proposed. That is, you would have maybe a monolayer or bilayers or multi-layers. You'll have a layered sort of system, but it'll be layered and it can be, we proposed actually a real, nice, there'd be a nice structure. Now, in reality, all formulations are actually of several components. And one reason for the several components can be that with your mixture of your two, you change the highest unoccupied molecular orbitals and the lowest unoccupied molecular orbitals. And so that can promote binding to a metal surface. And indeed, my colleagues, I'm also part of it, but my colleagues have a fairly elegant, nice paper on where that is and how that is. So you'll find, and it does actually, they didn't say, it does explain some things that we see when we use 2 or 3. Now, all of these are great approximations. The real life is a real, fancy and real tough microstructure and complicated sort of things. But this is what we think that is, or this is what I think. I do have a colleague and others who think that maybe you form, are interested in. He's always interested in maybe, like people found mica and a surfactant. You'll get micelle absorption onto mica. So that's another hypothesis.
Okay,
That's
thanks.
yeah. Again, the problem with all the studies is you don't have a nice surface. So, if you want to establish surfaces, it's like gold and all of that, which is, beautiful and no problem. The real system is a real complicated, so you need to do that. But people have done that, and you try to do best sort of surface science that you can.
And you're doing great engineering. Practical.
Yeah. No,
Yeah,
it all
sure.
has practical
Yeah, sure. Yep,
practical consequence. And that's
yep,
more, a lot of
sure.
it, frankly, it's because of that's what the company has experienced. Many
Sure.
people have worked many years. Your internal files have so many different things. And you have guys who know, oh, it worked there. So then, otherwise, if you're just just trying to do an experiment and then say, oh, it'll work here, that'll be much harder than having this actual practical things. I mean, for the first guys, it's most probably way tougher than for us. Yeah, thank you.
Yeah, thank you,
All
Sunder.
right, folks. Let's thank Sundar, and it's so nice to see everyone.
Yeah, it is so nice. It is really nice. It's nice to see you, Nitash. Nice
Same
to see
here.
you, Arul. Thank you for coming.
Okay, bye.
Thank you,
Bye.
Sundar.
Bye.
Bye.
Shailesh, nice to see you also. You didn't-
Yeah, my camera is not working, so. but,
Oh, and nice
And that's a good thing.
collaboration.
Trust me.
Thanks, Balsam.
Oh, Raghuvan's there also. Very good. Okay, I didn't see okay, fantastic. Raghuvan saw this talk. It's kind of recycled talk, but anyway. Yeah,
And I see.
yeah.
It's good.
Thank you.
Okay.
Okay, bye.
Bye then.
Bye. Stop
Bye.
sharing. Then I have to leave. Now I have to figure this out. Thank you. Bye. See you.